I wanted to do a quick video today for selective coordination. I was asked what selective coordination is, and I thought I would just do a quick video on what the basics of selective coordination is. Before I get too carried away with what it is, I just kind of want to point out why there may be some confusion about what it is. I think it's very important that we understand that the mandatory selective coordination requirements are not in chapters 1 through 4. Okay, we're not going to find this anywhere in 210 on branch circuits. We're not going to see it in Article 215 for feeders. We're not going to see it in Article 240 because 1 through 4 is generally going to be all premises electrical installations and not going to include selective coordination. Before I get too terribly carried away with what selective coordination is, I kind of want to go back to basics. Just say, let's go over the circuit conditions real fast, make sure we're all talking about the same thing, and we'll start with a normal circuit. Ohm's law states that current is directly proportional to voltage, but inversely proportional to resistance. That's really what the whole thing of Ohm's law is, right? So I equals E over R is going to tell me what my amps are in this circuit. If I have a 240 volt source, I have a 24 ohm load. I also have the resistance of my conductors, and that's going to end up in a normal circuit condition, 9.987 amps. I put a 15 amp fuse. I could probably run 14 gauge wire on this and everything would be totally normal. Everything's great. Then I have an overload condition where I have added another load. I've increased my amps to 19.96. I've only got a 15 amp fuse. At some point that fuse, that overcurrent protection is going to open and protect those conductors. These conductors are starting to get hot, and that is an overload circuit. The one I really want to talk about, the one I want to pay attention to here is the short circuit. If I do the same exact math, I use the same circuit, 240 volt source, but I have a short circuit. I actually go phase A to phase B or phase B to phase C. I end up with 7,742 amps. This is not an exact perfect math here because current is still going to take all paths, and this math is not showing the load, but it gets you the general idea, right? So more or less, I've got a phase-to-phase short circuit. I'm really just taking into account the resistance of the conductors with my voltage source, and that's going to leave me with 7,742 amps. So that's quite a bit. That 15 amp fuse should definitely blow. And selective coordination, we're going to get into that just a little bit more, but selective coordination is what that's all about. When I hit 7,000 amps, what happens? If I have a ground fault and I'm in the thousands of amps, I could potentially be, what happens? A ground fault, same thing. I have a hot conductor somehow touching or going to something that's grounded. I have an open circuit. I pretty much don't have any resistance. It's just infinite resistance, and therefore I have no current because, again, current is inversely proportional to resistance. To add to the confusion of what selective coordination is, this definition it can make your eyes glaze over unless you're really adept to this. It's kind of a mouthful. Localization of an overcurrent condition to restrict outages to the circuit or equipment affected accomplished by the selection and installation of overcurrent protection devices and their ratings or settings for the full range of available overcurrents from overload to the available fault current, and for the full range of overcurrent protection devices, opening times associated with those overcurrents. Right? So our overcurrent condition is what? Overload, short circuit, or ground fault, right? Most likely we're going to be talking about a short circuit or a serious ground fault in order to make selective coordination required or important. So like we talked about before, selective coordination is not necessarily just found in chapter 1 through 4. It's in chapter 5, 6, and 7. The article, of course, now in the 2023 has moved over to article 100. I don't know if it was always there or not, but it's there now in 2023. And this is kind of a general list of what it's for. Critical operation power systems. So we're talking about hospitals, 911 call centers, things of that nature. Okay, so here we go. I have on this slide a 15 amp breaker I added. Right here. If I have a 15 amp breaker and I have that fault that we talked about earlier, I have 7,700 amps coming to this fault. But what if I've only got 800 amp main breaker? My transformer is going to try to send 7,000, well, my transformer's not a power source, but we're not going to get into that. From the transformer to the first breaker, I could see 7,700 amps, and my 800 amp breaker could easily trip well before my 15 amp breaker. Okay, so I could trip this one off and kill the entire building. And now I have unnecessary power loss because I have a short circuit on a 15 amp circuit 4 stories up. So one simple 911 call operator could roll her chair over a cord, create a short circuit, and shut the whole building down. And that's not what we want. We want what's on the right side of the screen over here. If I have a fault on a 15 amp circuit and I have 7,700 amps, I do not want the 800 amp breaker that's the main or any of my 400 amp sub panels tripping, or my 200 amp that's ahead of it, or even my 100 amp sub panel. I don't want any of those tripping before my 15. I want that power to be isolated to the affected area. That's selective coordination in a nutshell, right? So we cannot assume the selective coordination is achieved if the upstream overcurrent protection device has larger ampere ratings. Okay, one of the other things here is in 2023, I think they've addressed this a little better than they did in the 2020 code, because now it also affects other feeders and branch circuits. So if you have any area that needs to be selectively coordinated, the whole place needs to be selectively coordinated. I don't have the code reference on that in front of me, but if you have the 2023 book, let's look into that, because it is it only makes sense that we're going to be selectively coordinating everything, not just those things that are in line with a particular area. What sense would it make if I only had to selectively coordinate these panels that were in purple, but all of a sudden I've got a janitor who plugs something in over here and trips off the 800 main, because this is not selectively coordinated. So the 2023 did a much better job about addressing what needs to be selectively coordinated. Inherently, series rated systems are not selectively coordinated. They can't be. A line side protective device has to open to protect the load side of the circuit breaker. Okay, so I cannot have a larger breaker ahead do all the heavy lifting to cover my short circuit current rating. I have to, I just can't have, I cannot have series rating with selective coordination. Let's just leave it at that. Okay, so time current curves. So selective coordination time current curve study, example from an industrial facility right here in Colorado. In order to verify compliance with the requirements for selective coordination, time current characteristic curves can be constructed to show the opening and clearing times of the overcurrent devices for all the values of overcurrents up to the maximum available fault current, which these devices could see. So in order to achieve selective coordination, there can't be any overlap on the time current curve at the fault current where, and that would be the problem. So coordination in this example is not mandatory per the NEC, but it was elected by the facility owners for the continuity of service. So I think this is a water facility in Commerce City. They didn't need to do selective coordination, but they sure wanted to maintain they had a continuity of service there. So this example is just to confirm the separation of trip curves for times beyond 0.1 second, and it would therefore comply with 517.31G. Okay, selective coordination, feeders supplying 2 or more elevators, critical operation data centers, emergency systems, legally required standby systems, and critical operation power systems, or COPS. Okay, and that's pretty much that. So while we're talking about this, there are such things as current limiting devices. Something that I've noticed, seems to be a lot of confusion, even on the part of many engineers, of what can and can't happen with current limiting devices. We'll often get plans in that say the let-through value of a fuse. Right? So I may have a short circuit current rating of 50,000, but the let through of my fuse is only 22. So the engineer is going to tell me, hey, it's okay to put a breaker in that's only rated at 22, even though I have a short circuit current that is much higher. Okay, and that's partially true, like many things in the National Electric Code. It's just partially true. So just because I have a fuse, if I have a short circuit current rating of 65,000 at this point, but he's telling me that my fuse will only allow 22,000, so don't worry about it. I can go ahead and put in a breaker or a device that's only rated at 22,000. That's kind of a misnomer. A lot of engineers will say that they can do this, and there is only one condition in which they can do so. Okay, and that is existing installations. They are not allowed to use the let-through current value in new installations. So you cannot do this. You can't design this. This has to be a last-ditch effort in an existing building to try to achieve safety. This is not our go-to. All right, so the degree of current limitation can be determined from the standards from the let-through charts, and the let-through charts are plotted from actual test data based on fault current levels, and the let-through charts are available from the circuit breaker and fuse manufacturers. That's who gives them. The engineers read them. I'm not disputing that it works, But the National Electric Code only allows us to do this in existing installations. Here it is. This is a series rating, 240.86 for a series rating. So if I have a device and I want you to look at, here's your options. If I have a series rating, I can go on A or B. I'm either allowed to select under engineering supervision in existing installations, I can apply the let-through current of a fuse or a breaker or whatever, or I can use a tested combination system. So if I am using a series rating in a new installation, the only option available to me is B. That's it. So I don't want to say that they can't do it. I want to point out some confusion about when they can do it. I say they, the engineers, when an engineer can use a let-through current, because the short circuit current rating in this example is still 65,000. And there's nowhere in the National Electric Code that says I can use a fuse let-through value in lieu of a short circuit current rating or value. I just can't do it. There's no code that allows these things to be. And just wanted to clarify that while we're doing this quick little video. This is an example of the up over down, Nintendo game that the engineers play. So you go up, over, down. So it's not just playing Contra and Nintendo, right? It's determining the peak let-through current. And this is how they would do it. The engineers would do it. Basically, starting the prospective short circuit current of 86,000 amps, proceeding up to the 800 amp fuse curve. Then they follow left to the instantaneous peak let-through current, and then read the peak let-through current at 49,000 amps. So if a fuse had not been used, the peak current would have been 198,000 amps. So can they do it? And as an engineer, absolutely. In an existing circumstance, this is how it works. But it is certainly not something that can be designed in a new system. And I just wanted to clarify that. So I think that's pretty much it. Wanted to go through those couple of quick things, and we will have a great day and see you next time. Thanks.